Okay, how's it going out there for SVVR 2016? You guys feeling good? Feeling pretty good? Nice, that's what I'm talking about. Sweet, so we're going to get ready for a talk for Dr. Fei, CTO, co-founder of uSens. He'll be talking about inside-out tracking for AR and VR, some human-computer interaction things. So always a fascinating topic, very excited. So let's give him a warm welcome to the stage, Dr. Fei.
Good afternoon, and thank you everyone for coming. Although the title is about inside-out tracking, but in the beginning of the talk, I will share my personal experience working on 3D visualization and working on VR in the past. Then I will lead to the new inside-out tracking for VR and AR. So yeah, I'm Yue Fei, CTO and co-founder of uSens, and my vision and my dream was always about making the digital world more realistic, natural, and interactive as the real world. And for VR, VR's evolution is from pro market to the consumer market, making it easier to use, can penetrate into average consumer. And so what we have done before, we have seen before, including 3D visualization, 3D desktop, 3D operating system. And we have seen room-sized VR systems. We have seen smaller table-sized VR systems. And we have HMD-based VR. And now we are making it a wearable device, very light, very inexpensive. So first, interactive 3D desktops. So when was the first one? I don't know the answer, but I knew the first one I knew was about 1991, the beginning of, so that was from Xerox, called Information Visualizer. Here, we are already seeing the element of 3D UI, the metaphor of bookshelf, and all the controls are here. And in the background, you can see 3D visualization of complex data structure. At that time, there's no, well, they didn't deploy it to HMD, but that's possible. It's designed for a mouse for a normal display. And in year 2000, Microsoft tried to have similar idea into operating system. It's called a research project called the Task Gallery. Okay. So user can easily manage many different tasks into a room-sized metaphor. User can walk a little bit in and out in the room. In 2003, Sun Microsystem project Looking Glass looks much nicer and much more consumer-friendly. It's written in Java. And also in the same time, about 2002 to 2004, I also founded my first company called Infinite 3D. And this is the one running on Windows using a native code, so a little bit faster and compatible with all the existing Windows applications. It is designed for VR and designed for 3D freehand interaction. So this is how it works. User can really zoom in out, and all the 2D applications are still interactive. It's backward compatible to old applications, but it do have new 3D metaphors, new 3D applications, like this. This is the manager of tasks or users' documents. And user can arrange the applications, documents, anywhere in the 3D space. Can be on the floor or hanging to the wall. Everything is interactive. Oops. And it gives 360-degree views to the user. User can rotate the head if they do have a HMD. So this is one more step into consumer-friendly 3D visualization, 3D UI. And how about, and around the time 2009, 2010, 3D displays becomes available. It's not HMD yet, but people, human eyes, can have a stereo perception of depth. So on that platform, I also tried to do something that make 3D display, 3D visualization useful for the average consumer. So there are 3 different components. One is how do they interact, the controller, and how do they see the depth, how to utilize the depth, help the human cognition activity, and how to give an immersive experience. So this controller consists of a touchpad. User can use touchpad to control everything, but also can use in-the-air gesture to grab things. There is also a side button to recognize other all 4 fingers actions. Here is the main view. In this view, we utilize depth. Actually, people can wear a 3D glass to look at this. Really have a very nice depth perception and utilize depth to encode history information. What's in the past are further away. What's current are closer to the user. Also using peripheral vision, actually new items are coming from underneath of the screen. So that's the human peripheral vision area actively catching the fast movement. And this user can go to a God's view to have a better understanding of the information structure. And the interface is larger than the TV. User can rotate the head to see different things. And in this view, we use depth to visualize real depth. User can understand the map better. Here, we use depth to visualize priority. This is a 3D, actually, calendar or task manager. What's closer to the user are more urgent tasks. And user can use natural gesture to go in and out, switching between the items, tasks. So those are the experiments of doing 3D OS, 3D UI. And another perspective of the VR is the hardware perspective. So we have seen in the pro market, room-scaled VR, like cave system. It is very accurate, but the DOF adopts, the degree of freedom that system can track is not very high. It can track, so here, on top of the head, there are markers. The system can track six off motion of the head. Also, user have handheld controller, also has markers. So the system can track 6-off motion of the handheld device, but not the full arm motion, not the fingers. So how to make this system go from government, big projects into small business, or average user can go in, immediately use it. So we did a system that utilize cheaper screens. Also utilizing a Kinect sensor that can recognize human body joints. So what we did here, we have a system to learn and interpret user intention, so that when user want to move forward, the system really allow user to move forward more than actually they do. User can also move backward. So in the limited space, user have larger range of motion. User can use the full arm gesture to measure the ground and to find the list of furniture that fit the ground the user measured. So what we learned is having higher DOFs, although their accuracy may be lower, but user perception, the easy to use is much, much better. It's a natural and a rich interaction. Every user can go in without any handheld controller, start to play. So what about table-based VR? One famous thing is not really VR, but it's Microsoft Surface. It is a big surface. User can see 2D objects, can operate in 2D. And there are companies making it 3D, like Z-Space. They have very accurate head tracking, very accurate tracking of the pen. People can really do engineering work on it. But the field of view is limited. The immersiveness is limited. It's not for average consumers to walk into a store to play with it. So we did something, it's called Tavala. It's a 3D virtual table. User can use natural freehand interaction. We process the depth data using computer vision algorithms to do hand motion recognition in 3D. Also have 6-DoF head tracking. So the principle is very similar to what Oculus DK2 and CV1 is outside-in tracking. And it gives user a very immersive experience. It's 120-degree viewing angle if user standing at the right spot. Here we see everything 2D, but actually when user wearing the 3D glass, everything is popping out of the table. It's holographic effect. Using in the air freehand gesture, now user walking to different directions, it can see things very realistically from different angle. And this system is more than VR. It's actually, here is a virtual shopping center. User can freehand really grab something, lift it in the air, and look at different angle. So by changing the interaction, by making better head tracking, hand tracking, we can make VR from a pro space into consumer space. Everyone can jump in and play, and a lower cost than the pro systems. So that's what we learned. And this system actually is more than VR because users still see the outside environment, still see the table. So it's more like a mixed reality, augmented reality. We see the real world, but on the table, magically something holographically standing up. And the user can also have a God view, see very deep environment. This is the opera. User can see deep down, something lower than the table as well. So what we learned here, 3D manipulation should be using freehand and direct onto the 3D virtual objects. And by combining this 3D visualization and the 3D interaction, we can have a holographic interactive experience. So we have covered, in the past, we have 3D OS, 3D desktop, have room-sized VR, table VR, and now we have HMD VR. And in the HMD, actually, we can realize all those things. Virtually, we can have a table there, or a room there, or any other visualization. And that's why HMD VR is making VR ubiquitous. But they have their own problems, like have a cable, it's not convenient. Also, eye strain is heavy. So from all those things we learned is in VR, what's most in common, all the VR in common, and the most important actually is tracking, and tracking. So what do I mean? Tracking, first, the richness of the tracking, not only few dots, but the full hand, full fingers, better be the body skeleton as well. The second, the quality of the tracking, the latency and the accuracy is still important. And third is interactivity, which I mean when people do the interaction, the virtual world should respond as a real environment. And in the future, the virtual objects should also give user physical nudges, physical feedback. So that's what I mean, interactive, they're two-way interactions. Okay, now to the topic of mobile VR. We all see mobile VR as the gateway to even bigger mass market of VR. And what we believe, what we are doing is lightweight interaction. So what do we mean? We mean lightweight, we mean 3D freehand interaction without holding any controllers. Because for a mobile system, users should be able to jump in and play. And 3D head tracking as well, users need that ability. And when having some of the hardware available, we can also achieve augmented reality using VR headset. In the future, there should be more tracking adding to the system. So, but there are also needs for, or requirements for mobile VR, easy to set up. So inside-out tracking is good for that. It's very easy to set up, zero setup. Other needs like power consumption. The tracking system needs to have low power consumption, low GPU, CPU usage, also lightweight. So these factors are against inside-out tracking. First, so 3D freehand interaction. Here is our video. So the system, this is educational, just sample application. User can touch the stars. The system really tracking the hand in 3D. User can grab something, then start to rotate it. And this is a game. User can dodge the bullets or even stop all the bullets like the Matrix movie. And here is the interface, the UI. User can also use 3D freehand interaction to touch those panels to select applications. And this is our algorithm. It is machine learning based, so that very difficult hand poses it can still recognize, like occluded hand pose. And more about augmented reality. When saying the end head tracking, right? So this is a demo using cameras mounted on top of a normal HMD. So the outside world we see are captured by the camera and projected onto human's eyes. But there are some virtual objects like the Tiananmen Square and the Golden Gate Bridge. They are virtual. And then hand tracking also working together in the system. So both hand tracking and pose tracking can work at the same time. Fast forward a little bit. Okay. Yeah, and what's neat about it is user can seamlessly switch back to the VR mode and also can keep some of the objects they created in AR mode, like those texts, bring them back into a VR environment. Okay, so far, what we see is in challenges in VR, including display, so that's more about optics and the EE problem. Rendering, that's 3D graphics problem. People are still working on it. Rotation, head rotation tracking, so that's signal processing, IMU. Problem is basically solved. Pose tracking, outside-in pose tracking is also basically solved using signal processing or using CV methods. But mobile head pose tracking, if using inside-out method, then it's heavily rely on computer vision. Hand tracking, if not using any gloves, then heavily relying on computer vision and AI. In the future, we also need environment scan, object recognition for AR. Again, CV and AI. Avatars in the virtual environment need to be smarter, more like humans. They need AI. They need to be improved a lot. And the computer should generate the virtual world to respond to us. That's also hard AI problem to solve. So the trend that we see is we are going, computer vision and the software part is going through signal processing toward CV, toward AI. So that's the general trend. So yeah, at uSens, we will have a tutorial session later today. And we will have developer network open June. We have SDK in Unity, Java, and C++. So, yeah, a little bit of advertisement. In the end, say we are hiring. So if you share the same passion, please, yeah, consider why not join us. Yep. Thank you. Now it's Q&A.
Thank you all for coming. Do we have time for a question or two, or? We have time for 2 questions. What we're going to do, if there's questions, I'm going to come to you so we can record them. Thank you, Dr. Fei. And thank you all for coming, too. Really appreciate this. Come back to the tutorial later today. We're at booth 421 as well. Okay, we got a question here.
What sensors are you using?
Yeah, basically the algorithm is sensor agnostic, can be depth sensor or stereo sensor. And right now we have demos. Those demos are using stereo sensor.
Time for one more. Anybody? Another question? Okay, we've got one more. And then feel free to come see. We've got engineers and the team over in the expo hall. Here you go.
Are you using any vision processor when you do the calculation?
So far in our demos, we are not using special processors. We are using the main CPU and the GPU.
All right, I want to thank the show hosts too, Carl and Donna, the SVVR crew. Thank you very much. Appreciate it. Thanks for coming.
Yeah.